Hello, my name is Anthony Webb, and today I'm going to be talking about the life cycle and eventual death of our solar system's yellow sun. To understand where the sun has been and where it will be in both the near and far future, we must first understand what exactly the sun is. The sun is one of many low-mass stars in our galaxy, a star born with approximately less than two solar masses of material. In comparison, intermediate stars have masses of between 2 to 8 solar masses, and high-mass stars are born with over 8 solar masses. Our sun lives in a sweet spot amongst other stars considering its temperature and condition so that we as humans can comfortably live here for many years. The first stage in our sun's long lifespan is found on what famed astronomers Hertzsprung and Russell named the main sequence. Our sun is near the middle of its approximately 10 billion year life as a main sequence star. Eventually, the sun will exhaust its hydrogen and undergo a series of incredible events that will ultimately lead to its death. The sun fuses hydrogen into helium with its core via the proton-proton chain, balancing gravitational equilibrium and energy in order to become a self-regulating solar thermostat that retains a steady fusion rate and a decent luminosity. It takes hundreds of thousands of years for energy released by nuclear fusion to travel from the sun's core to its surface, moving outward through a combination of radiative diffusion and convection. Once said energy reaches the photosphere or surface of the sun, it makes its way into space until reaching a given destination. Among main sequence stars, convection zones extend deeper and lower mass stars. High mass stars have convection cores but no convection zones near their surfaces. The life of a low mass star remains long and relatively uneventful as long as hydrogen fusion continues within its core. This minor yet constant rise in core temperature slowly raises its diffusion rate as well as its luminosity as the star ages, until nuclear fusion finally exhausts its central supply of hydrogen. We then enter the red giant stage. Without fusion to replace the energy that the star formerly radiated from its photosphere, the core will no longer be able to resist the inevitable inward pull of gravity, and it will then begin to shrink. The star's outer layers will now expand outward, despite the fact that the core will be shrinking under the crush of gravity. During this stage, the sun moves to the right on the HR diagram as it grows in size to become a subgiant. The star has inert helium cores and hydrogen fusing shells, until finally, as the expansion of the outer layer continues, the luminosity of the sun will then begin to substantially increase and its life track rises above on the HR diagram. Over the course of about 1 billion years, or about 10% as long as its life on the main sequence, the sun slowly but surely grows in both size and luminosity to become a red giant. At the peak of our sun's red giant stage, it will have become over 100 times as large in radius and more than 1,000 times as luminous as it is today. As the sun's core finally exhausts its hydrogen, it will then be made up of almost entirely helium, due to the fact that helium is the product of hydrogen fusion. However, the gas surrounding the core will still contain hydrogen that has never previously undergone fusion. As a result of gravity shrinking both the inert non-fusing helium core and the surrounding hydrogen shell, the star becomes hard enough for hydrogen shell fusion. This intense heat creates a buildup of thermal pressure inside the sun, pushing its surface outward until the luminosity is able to match the elevated fusion rate. Newly produced helium adds to the mass of the helium core, thus amplifying its gravitational pull and causing it to shrink. The sun's core and shell both continue to rise in heat as the sun becomes larger and more luminous until the core's temperature reaches about 100 million K. The sun has now become hot enough for helium nuclei to begin fusing together, and so it begins the next stage of its long life, the helium fusion stage. Fusion only occurs when two nuclei come close enough together for the attractive strong force to overcome electromagnetic repulsion. Helium nuclei have two protons and two neutrons, and therefore a greater positive charge in a hydrogen nucleus with its single proton. The greater charge means that the helium nuclei repel one another more strongly than hydrogen nuclei. Helium fusion only occurs when nuclei slam into one another at much higher speeds than those needed for hydrogen fusion, meaning that helium fusion requires much higher temperatures. As you can see here, the helium fusion process converts three helium nuclei into one carbon nucleus. Energy is then released due to the carbon-12 nucleus having a slightly lower mass than the three helium-4 nuclei. The last mass becomes energy in accordance with Einstein's theory of relativity, E equals mc squared. Gravity is counteracted by the sun's degeneracy pressure, and rising temperatures cause helium fusion rates to spike drastically. Its thermal pressure soon becomes strong enough to push back against gravity, while the sun's core begins to expand and pushes the hydrogen fusing shell outward, therefore lowering its temperature and its fusion rate. After having spent about 1 billion years transitioning and expanding into a red giant, the sun will then decline in both size and luminosity as it becomes a helium core fusion star. With fusion once again operating in the sun's core, it creates a similar balance than that of the one it had as a main sequence star, except now it is helium fusion rather than hydrogen fusion that keeps the central temperature steady. Because the helium core fusion in the sun is now smaller and hotter than it was as a red giant, its life track on the HR diagram dropped downward and to the right amongst the horizontal branch, the horizontal line of stars that represents a cluster of helium fusing stars on an HR diagram. After about 100 million years, which is only about 1% as long as the sun's 10 billion year main sequence lifetime, it will finally convert all of its core helium into carbon through fusion. As the core helium is exhausted, fusion will again come to an end, and the sun will once again go out of energy balance. The core is now made up of the carbon produced by helium fusion, and it begins to shrink under the crush of gravity. The exhaustion of the sun's helium core will cause it to expand once again, triggering helium fusion in a shell around the inert carbon core. Hydrogen fusion will continue in a shell atop the helium layer, and the sun will have now become a double shell fusion star. As both shells contract along the sun's inert core, their temperature and fusion rates become so high that the sun expands to a size and luminosity that is even greater than its red giant stage. The sun will go through thermal pulses predicted up with spikes in the rate of helium fusion occurring every few thousand years near the end of a low-mass star's life. The fusion rates in the helium and hydrogen shells last for no more than a few million years. With the carbon core unable to undergo fusion and provide a new source of energy, the sun will finally reach the end of its life. As the star's luminosity and radius rise, increasing amounts of matter flow outward with the star's stellar wind. During each thermal pulse, strong convection brings up carbon from the sun's core, enriching the surface of the star with carbon. The combination of a carbon-rich photosphere, low-speed stellar winds, and a gas temperature between about 1000 and 2000 K result in gas atoms sticking together in microscopic clusters and forming a small, solid particle of dust. The sun then ejects its outer layers into space, creating a huge shell of gas that expands away from the inert carbon core. The exposed core will still be very hot and will therefore emit intense ultraviolet radiation. This radiation will ionize the gas in the expanding shell, making it glow brightly as a planetary nebula. Over the course of about 100,000 years, The glow of the sun's planetary nebula will fade as the exposed core cools and the ejected gas disperses into space, leaving the carbon core behind as a white dwarf. White dwarfs are small in radius because they are exposed cores of dead stars, supported against the crush of gravity by degeneracy pressure. A white dwarf is therefore a little more than a decaying corpse that will cool for the indefinite future, eventually disappearing from view as it becomes too cold to emit any more visible light. The sun will continue to gradually brighten during its remaining time as a main sequence star, as it always has for the last 4 billion years. But in somewhere between 1 and 4 billion years from now, it will be bright enough to cause a runaway greenhouse effect, resulting in Earth's oceans boiling away and destroying our ecosystem as well as life as we know it. Temperature on the Earth will rise even more drastically when the sun finally exhausts its core supply of hydrogen, somewhere around the year AD 5 billion. And conditions will become even worse as the sun grows into a red giant over the next several 100 million years. Just before the helium flash, the sun will be more than 1,000 times as luminous as it is today, and this huge luminosity will heat Earth's surface to more than 1,000 K. By now, any surviving humans should find a new planetary home. It is projected that Saturn's moon Titan might be a new potential home planet. By this time, Titan's surface temperature will have risen from well below freezing to about the present temperature of our Earth. After exhausting its core helium, the sun will expand again during its last million years. As luminosity will soar to thousands of times what it is today, and its radius will grow to nearly the present radius of Earth's orbit, so large that solar prominences might consume Earth's surface completely. Finally, the sun will eject its outer layers as a planetary nebula and allow them to drift away into the interstellar void. In conclusion, our sun is currently here on the main sequence. It will rise and become a subgiant, then a red giant, then a helium-burning star, a double shell burning red giant, a planetary nebula, and ultimately a white dwarf. Thank you for listening. Merry Christmas and Happy Holidays.